Hi there everyone. Today we're going to be working on this problem that involves turning a fraction with complex numbers into the form of a plus bi, and we're going to do that using the concept of the complex conjugate. If you want to try this problem out on your own, feel free to pause the video and try it now, and I'll get started in just a second. So if you've seen a problem like this before, you probably know that we're going to need to use something called the complex conjugate of a complex number. So for a complex number, usually the basic complex number, we'll think of it in the form of a plus bi, where a and b are just real numbers. The complex conjugate is equal to a minus bi. And if this doesn't seem immediately clear why this is going to be helpful to us, let me just quickly explain. So what do we get when we multiply a plus bi times a minus bi? Well, if you know your FOIL rules, we'll be able to quickly determine that this is a times a squared, minus abi, inside is plus abi, and last, and this is the most important part, we're going to have bi times negative bi. So that's going to give us minus bi squared. Now, if we're to simplify this, what are we going to get? The a squared just stays the same. We have a minus abi and a plus abi. These cancel each other out. And then we're left with minus bi squared. Now, let's look into this a little bit further. All right, let's now look at just finishing this expansion. So this a squared is going to stay the same, and we're subtracting the expression bi squared. The square can just distribute to both of these terms, so that's going to leave us with b squared times I squared. And what can we do to further simplify this? Well, in this case, I isn't a variable like you might expect, like x or y that we normally see in algebra problems. I is actually an imaginary number, a numerical value that is equal to the square root of -1. If that seems sort of counterintuitive because you learned that the square root of a negative number doesn't exist, well, it does now. So welcome to higher level maths. And that number squared is just going to equal -1. Right? Because if you have a number that's equal to the square root of something, and you square it, that's just going to eliminate the square root. Square root of x squared is equal to x. So I squared is just going to be -1. So this expression here goes from a squared minus b squared I squared to a squared minus b squared times I squared, which is -1. So then this whole thing is going to just become a squared minus b squared times -1 becomes plus b squared. Now it's time to explain just why this whole process is relevant to solving the problem that we were given in the first place. So if you notice, we multiplied a complex number by its conjugate, both of which have an imaginary part, with I, and we are given the result of a squared plus b squared, where we know a and b are both real numbers. So the sum of their squares is also going to be a real number. And this is helpful to us because we can take this denominator that we have, 5 minus 2i, and use this strategy of multiplying it by its complex conjugate to give us a real number. But we can't just randomly multiply this denominator by 5 plus 2i and then solve it that way. We have to be a little bit more clever about it. So let's rewrite the complex number here. It's 3 plus 4i over 5 minus 2i. And we're going to use the classic trick of multiplying a fraction by another fraction, which gives us an equivalent fraction. So you've probably done this before. Multiply a fraction by something over itself. 5 plus 2i over 5 plus 2i. This is just equal to 1. So the result of this product of fractions is going to be equal to the original fraction. But the part that's going to help us is the fact that when we multiply this denominator, the denominator is going to become a real number. And at that point, it'll be in the form of a plus bi. So let's solve this. Let's do the denominator first, just so that we can confirm that it's going to give us a real number. 5 minus 2i times 5 plus 2i. And once again, we're going to FOIL here. So the first multiplication, 5 times 5, is going to give us 25. Outside is going to give us 10i, 5 times 2i. The inside is going to be minus 10i. Oops, let me just rewrite that I just to be extra careful. And this is going to cancel. And then lastly, minus 2i times 2i is going to give us minus 4i squared, which is equal to 25 minus 4 times I squared being negative 1, so it's going to be 25 plus 4, which is just 29. And now let's go through and do the top of this fraction. So the first is going to be 3 times 5 is 15. Outside is 3 times positive 2i plus 6i. Inside is going to be 4i times 5 is 20i. And then last is plus 4i times plus 2i. That's going to be plus 8i squared. And once again, we have an I squared. So positive 8 times I squared is going to become minus 8. Minus 8. So simplifying this part, the 15 and negative 8 is going to become a 7. And the parts that are imaginary, plus 6i and plus 20i, become plus 26i. Now, when we look at that result, 7 plus 26i divided by 29, this is in the form of a plus bi, because it simplifies to 7/29 plus 26i over 29. So a is equal to 7/29 and b is equal to 26/29. So here's our final answer. And overall, I just want to say, if you see something on a standardized test like the SAT or the ACT, which is of the form of a complex number divided by another complex number, just remember, there's pretty much a 100% chance that it is testing your knowledge of this concept of multiplying it by the conjugate of the denominator divided by the conjugate of the denominator to put it into a different form, to put it into the form of a plus bi. If you ever see something like this, this is the process that you're going to want to go through. And hopefully this explanation here of how it works and why it matters is something that you can remember and just automatically skip to this step here of multiplying something by the conjugate over the conjugate. And that'll make this process so much faster for you. And the last thing I'm going to do today is just to do another one quickly, just to show you how you can approach these problems and get them done as efficiently as possible. So let's make up another one of these. Let's just say we got 4 minus I over 6 plus 3I. How about that? So you get this problem. They say they want it in the form of a plus bi. So right away, identify the denominator, identify its conjugate, and multiply this whole thing by the conjugate of the denominator divided by itself. All right, what do we get next? So this turns into 6 plus 3i times 6 minus 3i, 36, and then the outside and inside distribution is always going to cancel itself out. And then up last you have minus 9i squared, so that's just going to turn into positive 9. So the denominator here is going to be 45. The numerator, we get 4 times 6 is 24. Outside, minus 12i. Inside, minus 6i. And then last is negative I times negative 3i is positive 3i squared. So that's just going to be minus 3. 24 minus 3, 21. Minus 12, minus 6, minus 18i. And in this one we have one extra step, because when we separate this into a plus bi, we would get 21 over 45 minus 18 over 45 times I. But both of these fractions can be simplified. So 21 and 45 both have a common factor of 3. So simplifying this would give us 7 over 15. 18 and 45 both have a common factor of 9. So that would give us 2/5. And that would be our final answer for this one. So you get a problem like this. You identify the denominator, create that conjugate fraction, multiply it through to turn the denominator into a real number, and then, if necessary, factor out some stuff to simplify that expression. I hope this explanation was helpful. Don't be alarmed if this is sort of confusing to you at first. I would say practice some. Think of some complex numbers of your own if you're trying to practice this skill, and you'll get the hang of it pretty quickly. So I hope this was helpful, and I hope you all have a great day.